Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 58, and it is entitled Magnetic Fields 2. In this lesson, we concentrate on magnetic fields and magnetic forces that are either created by or exerted on current-carrying wires, whether the wires are straight or whether they're bent into various shapes. We want to be able to calculate and describe the magnetic fields and the magnetic forces that are exerted on these objects. We begin with a historical experiment that was carried out by Hans Christian Ørsted in about 1820. Ørsted discovered that when he placed a compass needle in the vicinity of a current-carrying wire and the wire were oriented and the compass needle in the right way, then the current-carrying wire could cause the compass needle to twist in a different direction than in the direction of the Earth's magnetic field. In other words, moving electricity can cause magnetic effects, and that is a big deal. A young Michael Faraday in England heard about this experiment and explored it. If you saw the film Einstein's Big Idea, then you saw young Michael Faraday working in the lab of Sir Humphrey Davy and exploring the effects that current-carrying wires had on compass needles. And the way that we're going to describe it is the way that Faraday described it. He said that there were lines of magnetic force that surrounded a current-carrying wire. And we're going to sketch this as is done in your textbook. Let's suppose that I have a wire, which is represented by this green cylinder here, that's carrying a conventional current I in the upward direction. It turns out that there's discovered to be a magnetic field around this wire, and the direction of the magnetic field is given by another of the right-hand rules. If you have a conventional current, then you grasp the wire with your right hand with your thumb pointing in the direction of the conventional current. Then the fingers of your right hand wrap around the wire in the direction of the magnetic field. If it is an electron current that is being carried by the wire, then you would use your left hand and do the same thing. Grasp the wire with your left hand pointing in the direction of the electron motion, and then the fingers of your left hand will point around the wire in the direction of the magnetic field. The magnetic field lines form concentric circles, and the magnetic field gets weaker and weaker as you get away from the wire. So I'm going to sketch a few magnetic field lines for this particular current-carrying wire. This is a conventional current. If you're not told in the problem statement what the kind of current is, you should assume it's a conventional current. If I were to look down on this wire as it carries the current toward me, then I would see the magnetic field pointing in the clockwise direction around this wire. So what that means is if I brought a compass up and put it close to this wire carrying a current in that direction, then the north pole of the compass would point in the direction of the magnetic field. It would point in the clockwise direction around this wire. So if I brought the compass to the right side of the wire, it would point one way. If I brought the compass to the left side of the wire, it would point the opposite direction. But the direction the north pole would be pointing would be in the counterclockwise direction around the wire. Another perspective you'll see on this will be if you're looking at a wire head on. So let's suppose that this black dot here represents a current-carrying wire with a conventional current that is coming toward me out of the page. If I were going to sketch the magnetic field lines around this wire, then I would imagine grasping this wire with my thumb pointing in the direction of the current, and my fingers would point around the wire in the direction of the magnetic field. In this case, it would be in the counterclockwise direction. Now, we want to be able to do numerical work with this. So let's imagine that I have some point which is a distance r away from the center of this wire. What would be the magnetic field strength at this point P that's a distance r from the wire? This is a formula you're going to have to memorize. The strength of the magnetic field at point P is going to be equal to mu naught times I divided by 2 pi r, where mu naught is a number that's called the permeability of free space, or the permeability of the vacuum, and it has a value of 4 pi times 10 to the minus 7 Tesla meters per per ampere. There's a fascinating history about where this 4 pi number comes from. If you're interested in hearing about it sometime, when you have some time, come by and I'll be happy to tell you the story. But it's not something we're going to discuss in class, nor that you need to know for the AP exam. Many times these wires are going to be bent into loops. We want to be able to figure out what the direction of the magnetic field is due to a loop of wire that's carrying a current. So I want you to imagine that this diagram that I'm drawing here represents a coil of wire where the wire has been wrapped around several times in several loops. And the number of times is going to be important sometime. For our purposes right now, it's just multiple loops. This wire can carry a current if I hooked it up to a battery. Say, let's make the positive terminal on the left side of this wire and the negative terminal on the right side. And now a conventional current would flow up the left leg and down the right leg, and then it would flow in the clockwise direction. Generally, we're going to be interested in what the direction of the magnetic field is inside the loop of the wire, because that's where the magnetic field is going to be strongest. It's going to be strongest right in the center of the loop. So imagine I do my right hand rule again. Imagine that I grasp this coil of wire with my right hand in the direction, with my thumb pointing in the direction around the wire. In other words, my thumb is going to be pointing in the counterclockwise direction. The fingers of my right hand are going to be pointing into the page in the middle of the loop. So the direction of the magnetic field in the center of this loop is going to be into the page. Sometimes you might be interested in knowing what the direction of the magnetic field is on the outside of the loop. The direction of the magnetic field on the outside of the loop is going to be out of the page. Now let's solve a numerical problem. This problem is not found in your textbook. In fact, none of the examples in this lesson are found in your textbook. I thought to try to give some different examples for these problems. An electric wire in a wall of a building carries a DC current of 35 amperes vertically upward in the plus Z direction as shown in the diagram. What is the magnetic field magnitude and direction due to this current at point P, which is at R equals 7.5 centimeters to the right in the plus X direction? Indicate the direction according to the given XYZ coordinate system. They didn't tell us whether this is an electron current or a conventional current. So we're going to make the assumption that this is a conventional current. Let's do the direction first, and let's use our right hand. I would point the thumb of my right hand upward, and I would imagine grasping this wire, and if I were to look down on the wire, the direction of the magnetic field would be in the counterclockwise direction around the wire. Now I'm interested in that direction at point P. Point P is right over here, which is to the right of the wire, and I want to know at that point in this XYZ coordinate system what the direction of the magnetic field is. Well, if I look at my magnetic field lines, I'm going to see that at this particular point, the direction of the magnetic field is into the page. That means it's going to be in the minus Z direction. If the point P had been on the left side of the wire, then the direction of the magnetic field would have been in the plus Z direction. You're going to need to learn to be able to recognize these sorts of diagrams here, coordinate systems, and be able to say what the directions of certain vectors are according to those coordinate systems. Alright, so now let's calculate what the strength of the magnetic field is. And we use this equation that we have. B is equal to mu naught I over 2 pi r. And now I can just put in the numbers, but let me caution you that you need to write your numbers in MKS units. So you're going to have to convert that centimeters into meters. I get that the strength of the magnetic field is 9.3 repeating times 10 to the minus 5 Tesla. You can see that this magnetic field is not very strong. In general, magnetic fields are not going to be strong quantities. The next topic we want to take up is the force that's exerted on a current-carrying wire by a magnetic field. We've already talked about the force on a charged particle moving in a magnetic field. That's called the Lorentz force. Let's remind ourselves of that. We used a right-hand rule to determine the direction of the force. We let the fingers of our hand, if this is a positive charge, we would use our right hand. If it were a negative charge, we would use our left hand. Their fingers would go in the direction of the charge motion, which in this case is in the direction of the velocity v. The open palm is in the direction of the magnetic field b, and our thumb would point in the direction of the force. Now, if I take and confine these charges to a wire, it turns out that there's a force that's exerted on the wire in the current carrying magnetic field. Here's a video showing the force exerted on a current carrying wire in a strong magnetic field. So you see a 12-volt battery. There's a switch which can cause the current to flow a long wire, and that long wire passes between the poles of a strong magnet. The battery is connected. When the knife switch is thrown in one direction, you see the wire jumps out from between the poles of the magnet. And when pulled in the opposite direction, then the wire is pulled downward. If you've never seen that demonstration before live, it's really something worth seeing. Now, let's write down what the strength of that force is. There's a formula for it, and here it is. Let's say that I have a wire that carries a current I that's in the presence of some magnetic field whose strength is B. Then the force on this current carrying wire due to the magnetic field is given by this equation. The force is equal to I times L, the length of the wire, cross B. And this vector L means the direction that the current is flowing in the wire. This is a cross product, which means that the maximum force that's going to be exerted on the wire will be when the direction of the current, the wire, L, is going to be perpendicular to the magnetic field. The force in magnitude is going to be I times L times B times the sine of the angle between L and B. And the direction of the force is going to be the same as the direction of the force in the Lorentz rule. I'm going to put my fingers in the direction of the charge motion, in other words, the direction of the current I. I'm going to put my open palm in the direction of the magnetic field B, and then my thumb will point in the direction of the force that's exerted on the wire. So in this case right here, for this wire that's carrying a conventional current to the right with a magnetic field that's into the page, then what I would see is that the force on this wire would be exerted in the upward direction. So in this coordinate system that I just sketched here, this is going to be a common one that you'll see over and over again in these problems and maybe even on the AP exam. Then the current in this particular situation is in the plus X direction, the magnetic field is in the minus Z direction, and then the force on this wire, if it's carrying a conventional current, is going to be in the plus Y direction. So let's do a numerical example now. You won't find this one in your textbook, but it's a good one in any case, and it also combines something from electricity. You'll find many of these problems on the AP exam will combine several topics at once. In the circuit shown, a wire of resistance 25 milliohms is connected to a 22-volt battery. A length of 15 centimeters of this passes between the poles of a bar magnet whose magnetic field in the vicinity of the wire is 1.2 Tesla. Calculate the magnitude and the direction of the force exerted on this wire. You may assume that the current and the magnetic fields are at right angles to each other. And in order to figure out the force, I've got to know the direction of the current and I've got to know the direction of the magnetic field. Let's start with the direction of the magnetic field. How do I find the direction of the magnetic field, say in the case of this bar magnet? The direction of the magnetic field is defined to be the direction that a north pole of a compass points when it's placed in the field. So let's figure out where this wire is passing through this magnetic field, which the direction of the magnetic field would be. So I'm going to go up here to the wire where it passes between the poles of this bar magnet. And now let's imagine I put a compass needle in there. Which way is the compass needle going to point? The north pole of a compass needle is going to point away from the north pole of this bar magnet and towards the south pole. So in this drawing that I've got there, the magnetic field is to the right. So there are magnetic field lines that are passing from the north pole of the magnet towards the south pole of the magnet. That's the direction of the magnetic field.